All right, everybody. Thank you for joining me for today's nTop Live. I'm going to be talking to you about a fantastic new integration we have with modeFRONTIER. So this is going to be all about nTopology and modeFRONTIER and how we can leverage this wonderful software to help out some automation processes. And specifically, we're going to be focusing in on a topology optimization workflow. So we're going to be taking a look at our design space, and over here on the right, you can see an image of the assembly. And the design space we're interested in is the bracket of this robot arm. That's what we want to optimize here. And the goals are to maximize the stiffness while minimizing the displacement and the mass, right? We're trying to lightweight this, but make sure it's as strong as possible. We're actually going to be using ANSYS FEA to perform our validation simulations. In this case, we're going to be using that external validation, and we're going to be running an automated DoE with modeFRONTIER to find the most optimal solution using statistical techniques. So we're going to be doing a lot of interesting things. And the overall workflow today is going to look something like this. We're going to be doing the topology optimization and the geometry reconstruction inside of nTop platform. We're then going to be meshing and passing that mesh over to ANSYS, where it's going to run a static structural simulation, give us our maximum minimum stresses, our deflections, and all of that sort of information. And what modeFRONTIER is going to be doing is taking all of this and automating for us, right? We're going to be running headlessly because nTop CL is headless. We're going to be running in parallel. That's a really nice thing as well. And we're going to be running 150 iterations of this. So let's take a look at the file a little bit. And this is our nTop file. We have our assembly here, and I said this is the part that we are interested in. And we're going to be going through a topology optimization process. That means we're going to be turning things into a mesh. And in the end, we're going to be post-processing our result until we have something what I would call a usable result. So we have nice, smooth geometry, good, sharp connection features, and a usable result. We are then going to be meshing it inside of nTop platform, and you'll see this export static analysis block here. So we're going to be applying its boundary conditions and directly exporting this into ANSYS file format, which we will then be using ANSYS Workbench to run our analysis to get the stresses in this part, right? And this topology optimization process has so many knobs that you can turn, right? And the reason for this study is to find the best combination of these knobs, right? So we have three main ones we're interested in. We're interested in the boundary penalty, the volume fraction, and the volume threshold. Those are the three that have some of the most significant impact on the optimization process itself. So those are the three knobs I want to turn, and I want to find the best values and the best combination of values for these three. All right, so you can see we're going to run through the process. We're going to be changing these three, and every single time we're going to be exporting that new design over to ANSYS. And for a little proof in the pudding, here is our design inside of ANSYS. We've run our static analysis. We have our von Mises stress. We can see our maximum spots. We have total deformation. We have access to all of that information. And then what we're going to be doing is using modeFRONTIER to automate this whole thing. So here is my workflow set up in modeFRONTIER. I have my nTop node in this case. I have the boundary penalty, volume fraction, and threshold all feeding into that. We're pulling out mass and volume information, and then we're passing that external simulation over to ANSYS, running that analysis and yanking out the maximum stress, total deformation, equivalent stress, and all of that sort of information from there. So we have a lot of information, and this is where we're going to be automating it. We're going to be setting up a DoE table here. And let me show you a quick image of that. We're going to be setting up a DoE table. We set our bounds in this case. We have here an upper bound, lower bounds for our three things. So we're going to be varying our boundary penalty from 0 to 1. We're going to be varying our volume fraction from 0.1 to 0.5 and our threshold from 0.1 to 0.55. Now, these have been chosen specifically based upon my knowledge of the process and the fact that I put the file together in nTop and I know about the right bounds to use to get proper designs, right? So just a little bit of manual work up front, and then we automate the rest of them, right? Do it once, automate it 150 times. That is the idea here. we're going to set up our DoE table. We're going to make use of a uniform Latin hypercube distribution. So we have only a few parts that have similar ones. So we have a proper distribution, right? We don't want any overlapping designs. That's not going to help us zero in on the right answer here. And then you can see here my boundary panel, or sorry, my DOE table that modeFRONTIER generates. You can see all of my changing values. And then what's left but to run this whole thing. So we're going to run this whole process, and we're going to go into modeFRONTIER again. I'm going to switch here. If I go over to my design space, we run this whole process. It's headless. It's hands-off time, right? You set it up, you let it run. And total, we run 150 of these, and each one takes about 20 to 30 minutes in nTop and about an hour to an hour and a half in ANSYS. Now we are running 4 in parallel, which is pretty awesome, but that's still going to take 48, 50 hours total to make 150 designs. So that's 48 to 50 total hours where I don't have to be working, your engineers don't have to be working, you don't have to be working, and you just come back to be able to evaluate these designs, right? It's a lot better than trying to do this by hand. In fact, you wouldn't even think about doing 150 designs by hand. But now we can see here on my curve, I have my total deformation average. I have my mass. You can see these are my high mass designs, high deformation designs. And I can see that my lowest mass and lowest deformation designs are going to be right on the edge of this curve. And I can, come here and check out my different types of charts. I can do all sorts of different things with modeFRONTIER and their wonderful post-processing of the results tools, right? I can do all sorts of different things in here, how everything is linking together, right? I'm certainly not an expert in modeFRONTIER. If you need an expert in modeFRONTIER, well, you'll go to Esteco and talk to our fantastic friends over there. But once we have all our results, what we need to do is evaluate these designs a little bit. So I'm going to choose about 5 to 6 designs, and we're going to take a look at this file here. So I have 5 designs that I chose on that frontier of my curve, right? The ones with the least amount of mass but the least amount of deformation. And I'm going to visually inspect a few of them because I might find something that I don't intuitively like in these designs. So I have here my 5 designs, design 6, 9, 87, 92, and 117. And I'm going to look at all of them manually. And I can see here, this is a pretty interesting design. I have some nice beams going on. A lot of material has been reduced in here. This is a pretty interesting design. Maybe I'm not a huge fan of this hole here, but it's not too big of a deal. This is a pretty good looking design. What I'm going to do now is overlay design 9. Design 9 is blue, and you can see how changing these values just a little bit can result in a fairly different end result here. So I have different areas where my material is forming. I have the beams that are in slightly different locations. This hole up here has now closed up in this case, right? So that's pretty interesting. But overall, it's also a pretty good design, right? Pretty nice looking design. But we got rid of that hole that I didn't really love. We look at design 87. Sorry, overlay that on there. So that's green. So this is pretty similar. This is a pretty similar result, even though it has different values in there. But if we look at it, this beam was trying to form, but it couldn't quite get there. And intuitively, I don't like that, right? And I'm going to go through the rest of these, do the same idea. 92 also has that problem with the beam, but it's very different now, right? Look, there's a hole here. There's a beam here that just wasn't there in any of the other results. So you can really see how these start to change. And once I get a feel for that and I like it, right, I'll zero in on design 6 and I think 9 here. And then we can go back and kind of look at their actual results. So we can start comparing them against each other. So we have design 6, and maybe I had that mislabeled. It's actually number 87. But we can look at them and compare them against each other and against the original. So the original mass was 36.42 kilograms. And for design 6, we're at 12.98. So we're nearly at 1/3 the overall mass. And that is pretty impressive. Design 87, a little bit heavier, sitting at about 14 kilograms. That's just a little bit heavier. If you look at displacement, what I've done here is not looking at the displacement of the original one, but comparing the displacement between my 2 optimized results. And even though design 7 weighs a little more, it deforms less, right? Design 6 has 5% higher deformation than Design 87. So now we need to decide what's more important to us. Is this enough weight and we need less deformation, or is this just too much deformation in total, or can we live with the extra deformation to reduce the mass further, right? This comes down to your situation here. And you can see I'm showing you just how different my input values were to get to these two different results. And this is the idea. I didn't have to manually change all of these different values to get to my end result. I probably would have never zeroed into anything close to these values here. And that is the power. Now, the real power is not in my results here, right? This is a nice case study, right? A good example, but the power is in this integration. It's not the fact that I reduce the mass of this part. It's the fact that you can take this idea, take this template, if you will, of designing with nTopology, automating with modeFRONTIER, and getting the best possible design, and you can take it and fit it into your situation. So maybe you have thermal considerations as well as structural. Maybe you have also some magnetic field considerations you need to take into account. You can hook this up to whatever you need to and run these, complex optimization problems automatically and headlessly. That's the power here. So, to recap, this fantastic integration really allows you to take advantage of nTop's unbreakable geometry kernel and then optimize for whatever you need to. It's a fantastic new integration. If you need to learn more about this, I did a full webinar with the wonderful people over at Esteco. You can find that on our webinar page or down below. Thank you all for watching. I had a fantastic time talking about this process. And as always, if you have any questions, reach out to us and we are happy to answer them. Thank you.